We will be looking at question 20, October 2021 paper. This question is to do with free energy and partial pressures, Kp. So let's have a look. It starts off referring to a chemical equilibrium, and nitrogen monoxide and oxygen react to form nitrogen dioxide gas. You've got the equation there. In the reversible reaction shown equilibrium 20.1. You've also got delta H, and you've also got delta S, entropy change. Now, it gives you one feature of dynamic equilibrium, which is a closed system. State one other feature of dynamic equilibrium. You see, with equilibrium, one example you can use is like a can of Coke or a fizzy drink, and you've got your little atmosphere of a gas in here, and here you've got the dissolved gas. The can is a closed system, nothing goes in, nothing goes out. The rate of the gas dissolving into the solution equals the rate of gas being given off by the solution. So we can say that the rate of the forward reaction is equal to the rate of the reverse or backwards reaction. This is one feature. The other feature is you see the amount of moles or the concentration of the reactants and the concentration of the products, whatever they may be, remains constant. So concentrations, this is an or. You could write this: concentrations of reactants and products remain constant. The mark scheme specifically says, do not allow the same. Are the same. No, no, no. They are not the same. They are constant. Constant means not changing. That's what it means when it's at equilibrium. It says, show that the formation of NO2 is in equilibrium 20.1 is feasible at 25 degrees Celsius. So when we're looking at feasibility, we're going to look at this equation, delta G is equal to delta H minus T delta S. Now, feasibility at 25 degrees Celsius, so let's plug these values in. Delta H is given as 114 minus T is going to be plus 273. Let's convert that to Kelvin. That gives you 298. So that will be 298 multiplied by, you see the entropy change. The entropy change, if you look at the units, is joules per mole per Kelvin. We need it in kilojoules. So we need to minus 147. We need to divide that by 1,000. This is a point that catches students out, the conversions. It's because of this over here. Need to convert to kilojoules. This gives, let's work this out. minus 70.194 kilojoules per mole. And you see, because this value, because delta G is less than 0, the reaction is feasible. If it's greater than 0, it's not feasible. Okay? 1 mark for the calculation. 1 mark for the calculation, and 1 mark for these 2 points here. Next question. Determine the maximum temperature in Kelvin for feasibility. Sometimes you see questions where they say, determine the minimum temperature. Why is maximum temperature here mentioned? Let's look at the expression. You see delta G is equal to delta H minus T delta S. And you see, looking at these two values they've given us, both of them are negative. So let's plug these in. This is a negative value, delta H, minus T multiplied by another negative value. So you see, as temperature starts to rise, because you've got a negative and a negative, if the temperature gets too high, then this becomes greater in magnitude than the delta H. That will give you then a positive delta G value, not making it feasible anymore. So by rearranging the equation, we can work out what that maximum temperature is. So we assume delta G is equal to 0. And so we rearrange, bring T delta S to the other side, and then divide both sides by delta S. So T will give you delta H over delta S. And plugging the values, minus 114, which is delta H, divided by 147 divided by 1,000, minus 147 over 1,000 to convert to joules to kilojoules, and that will give your answer in kelvins. (775.51). Appropriate number of significant figures, give 3. So that will be 776 Kelvin. And why is 3 sig figs appropriate? Because if you look at the supplied data is also 3 significant figures. That's how you can make that choice. Okay, moving on. This is a KP calculation question. NO, equilibrium 20.1. Let's just write this down. NO, O2, NO2. NO plus O2 and NO2. So it tells us that the chemist mixes 1.60 moles of NO, 1.50 moles of O2 in a container and allows the mixture to reach equilibrium. We are going to use the ICE table. What does ICE stand for? Initial, change, and at equilibrium. So we've got 0 amounts of the product. This is in moles. It tells you at equilibrium, 75% of NO has been converted to NO2. 75%. So what's 75% of, first of all, is it balanced? 2 and a 2. We need a 2 there and a 2 there. So it's a 1-to-1 ratio. What is 75% of 1.60? 75% has been converted. That means you are 1.20 is being used up. That means 1.20 is being formed. Because nitrogen oxide and oxygen are in a 2-to-1 ratio, that means half of 1.20, half of that amount is the oxygen reacting. Half. And what's the remaining amounts at equilibrium? 0.40, and this will be 0.90. And we've got our equilibrium amount here. This is the amount in moles. And because we're dealing with partial pressures, you've got the total partial pressure, and it wants us to work out the Kp in megapascals. That's the units per megapascals. So that will be, first of all, we need to work out the mole fraction. What is the mole fraction? The mole fraction is the individual amount in mole divided by the total number of moles. This all adds up to, yeah, no. This adds up to 2.50. Let's just double check that. 2.1, yep, 2.5. So 0.4, let's divide that by 2.5. Divide that by 2.5. Divide that by 2.5. And the mole fraction will be and you see these mole fractions need to add up to 1. So that will be, yep, that adds up to 1. And now the partial pressure is going to be the mole fraction times total pressure equals the partial pressure. The total pressure is given here. And so let's multiply these values by the total pressure. 0.16 times 1.21. We have our partial pressures. And what we do is now plug them into the expression. So our expression is Kp is equal to products over reactants. Our products are NO2, so P, we use the curved brackets, NO2. We square it because we raise the big numbers as powers, products over reactants. Oxygen's partial pressure. And plug in the values. By plugging in the values, let's see what we get. three significant figures. The answer is 20.661157. Three sig figs will be 20.7. Yep, if you look at the mark scheme, it says if answer is 20.7, award all 4 marks. Moving on. Right, for this question, the chemist repeats the experiment 3 times, makes one change, but uses the same initial amounts of NO and O2. Before we begin with this question, let's rewrite the equilibrium. NO plus O2 gives you NO2. You got the big numbers. You see Kp is only affected by temperature. So temperature, Kp is either going to increase or decrease. Now, you see this, the Ford reaction is exothermic. The Ford reaction is exothermic. If the Ford reaction is exothermic, the reverse reaction will be endothermic. So by increasing the temperature, to oppose that change, is going to try to, the equilibrium system is going to try to bring that temperature back down. The only way it can do that is by going in the direction, in the reverse direction, because the reverse reaction is endothermic. So actually Kp at a higher temperature will be smaller. Kp is not affected by anything else, only by temperature. So we just say same for pressure change, same for catalyst. Now, by increasing the temperature, the equilibrium shifts to the left-hand side. And so the equilibrium amount of NO2, which is this, is going to be smaller. By increasing the pressure, the equilibrium system will shift to the right at increased pressure. Why is that? Because there's 3 moles of gas on the left-hand side, 2 plus 1, and there's 2 moles of gas on the right-hand side. So the gas is a 2 moles of gas. So increasing the pressure, equilibrium will shift to the right, increasing, making the equilibrium amount greater when you increase the pressure. When a catalyst is added, you see what does a catalyst do? It speeds up the rate of reaction, but it speeds up the rate of the reverse reaction and the forward reaction by the same amount. So the equilibrium amount is going to be the same. The rate, the initial rate of the reaction, initial rate when you're reacting NO and O2 only, right at the beginning, at a higher temperature, is going to be greater. At a higher pressure, it's going to be greater. Using a catalyst, it will be greater. All these increase the rate of reaction. That is the end of that question. I will see you tomorrow.